Susan. Can you guys hear me fine? Okay, awesome. All right, thank you so much for attending my talk today, and it's such a pleasure to standing in front of you and share my thoughts on machine learning projects. And special thanks for Susan to make this track a reality. So a little bit about myself. I am very lucky to choose machine learning as my field 10 years ago. And after that, I've been staying in the industry as an applied scientist and machine learning engineer, more towards the modeling side. And currently, I am a senior machine learning engineer at Grammarly. Beyond the work, I teach deep learning at University of Toronto certificate program. This year, I also co-founded the Toronto AI Practitioners Network. It's a local AI meetup groups that we have that we invited hundreds of practitioners to talk about AIs together, exchange ideas, so on and so forth. As you can tell from the topic of this talk, this is a very opinionated talk. So I just want to make a very quick disclaimer. All the opinions are my own. It's not related to any of the organizations on the list. All right, so let's do a quick activity to warm up the room. The first question is that, could you raise your hands if you worked on any machine learning projects before? Okay, that's quite a lot. That's good to know. Thank you so much. And the second question, a tougher question, have you worked on a machine learning projects that failed to go to production? Okay, thank you for being transparent. I see a lot of hands. Thanks for being together with me on this one. Yeah, so reflect on my own journey. I worked on machine learning projects across a couple of different domains, social media platforms, fintech solutions, and productivity tools recently. Well, some of them succeeded in reaching to production, many of them didn't. And even though each project taught me something interesting and I was able to learn some fancy technologies, it's not the best feeling of the world that the project you pour your heart into ended up generating the impact that we hope it for. So that motivated me to explore a crucial question, like, am I alone in feeling that way, and how severe is the problem? So it turned out that there's a couple surveys that are being done on this topic, and while older studies reported failure rates as high as 85%, most of the recent data tells a fairly similar story. So for instance, the graphics I show here is the study being done by Rexer Analytics back in 2023. You can see that they did a study on over more than 300 machine learning practitioners, and more than 32% of them said that their project, only 32% said their projects reached to production. So the exact number may vary from industry, depends on where you work. A lot of the big tech companies, they've been adopting AI for quite a long time. So there's a lot of experience being learned there. But for traditional industries, like banking industries or enterprise or startups, their journey is still ongoing, and they're still navigating their path towards a more effective and seamless AI adoptions. Before we dive into concerns, I just want to recognize something that not all the failures are inherently bad. So machine learning projects often carries with very, very high uncertainties because it's experimental. Many of the times we can't draw a conclusion if something can be fixed by machine learning or not before we really get our hands dirty, exploring the data and try some baseline models. So if your team is able to conduct some preliminary studies and quickly identify there's not enough positive signals for you to invest further into the production, you decided to pivot or you decided to kill the project, this should actually be considered as success instead of failure, and it should be celebrated. This principle has been adopted everywhere, called fail fast, and I think it's crucial for encouraging good innovation to happen in the company too. And for today's talk, we'll be focusing on bad failures. By bad failures, I mean that projects drag too long to conclude without a clear definition, and the models that never went to production, even though the performance is pretty good. And lastly, the solutions that fail to get adopted even after we apply the model to production. So here comes the gold question we want to answer today. What leads to the failures of these machine learning projects? So this is the agenda for our today's talk. We'll start with a quick overview of what a machine learning project lifecycle looks like and how it's different from ordinary, software projects. Understanding this process will be helpful for us to see where exactly are these failures occurs. And then we'll dive into the 5 common pitfalls with the examples and some of my thoughts, like where can we reduce the chances of encountering those problems in the future. And lastly, we'll wrap up with a summary. All right, let's take a look at the machine learning project lifecycle. On the diagram here, it shows the 6 steps of the machine learning project lifecycle. Just to be fair, this is a high-level simplified overview. So the details are, the devil is in the details that we're not showing here. Usually, we start with identifying what is the business goal that we want to try to optimize, and we need to frame a machine learning project based on this business goal. Once we have outlined machine learning problems, we need to get into the data, exploring it, processing it, so we can use the process data to train different models. Once the model is trained, hopefully you'll find a candidate model that we consider as performing good enough that we want to deploy and use the production line to monitoring how the model performs. And the feedback we got from the monitoring process will be used to refine the entire system. That's how the iteration is happening. There are 2 obvious points that are worth mentioning. The one is the lengthy multi-step process. There's a lot of handovers happen between steps and across team, and naturally this increases the risk due to this complexity. And second is that machine learning projects are data-centric optimization problems, and these feedback signals, no matter it's from the model, from the data, or from the monitoring process, are the essential component we want to make sure we leverage if we want to work on a successful project. For the 5 common pitfalls that we want to cover today, the first pitfall that I would like to discuss is honestly one of the most critical ones, is working towards optimizing a wrong problem to begin with and ended up wasting a lot of time and effort. Is that a common thing or not? Let's go back to the survey we have done here. So from the figure, what it's showing is that when people were asked how often are project objectives clearly defined before project initiation, 29% of them answered that they begin with a clear definition, and the 26% of them said that rarely this thing happens. This lack of initial clarity is definitely a common battle that machine learning engineers fight before we really committed to working on one project. Well, iterating over business goals and bearing with some ambiguity to start a project is actually pretty common in the past, right? And for machine learning projects, why this becomes a more severe problem? And in order for us to understand that, we need to explore how business goals is being turned into a machine learning solution. So of course, we don't want to miss the first step, which is identifying whether this is a machine learning related problem or not. Many times you may be able to find a rule-based solution that works pretty well, or you can just incorporating some operational changes to your system rather than trying to explore a machine learning solution from the beginning to the end. Once we make sure this is a machine learning problem, this goes to a big translation steps. There are I think the front is a bit small. There's a couple of things happening. For us to solve a machine learning problem, we need to identify what are the specific data that allows us to extract the signals from. So that is some heavy lifting from the data engineering team. Second is that we need to train usually a whole bunch of different models, including different model architectures, including using different hyperparameters, in order for us to find which model works fine. And this, if we're talking about training a more sophisticated models, this usually involves in using expensive infrastructures, including GPU. And at the end of the day, what we're trying to optimize is a mathematically defined objective function. This objective function is highly dependent on what type of business goals we're trying to solve. As you can see, previously, the pivots or the iteration of business goals may not cause a lot of issue. But right now, if we ever want to iterate on that, the data, the objective function, and even the entire machine learning pipeline might need to be updated because of that. And that often results in a significant amount of work being tossed away. And that's why, to begin with a good machine learning problem, we usually want to ask a lot of questions to make sure the business, the team is pretty dedicated into solving that particular problem. So here's an example that I want to share with you. In terms of how can we increase our chance of picking a winning project to begin with. This is based on my past experience working in a fintech company for over 5 years. The organization I worked with adopted this centralized AI resource model. Means that all the team will go to this team to find some AI support. And this model is quite common in these days because the shortage on AI talent is still a thing for many companies. We can't afford having an AI team in all the business lines that have an AI use case. This gives us some unique advantages, but also some challenges too, because all the business lines will come to us and saying that their project is the most important one we should looking into, and we should prioritize that. Often using some financial jargons that we may or may not understand. So our team need to develop a special type of skill to navigating through all this noise and identify which project is the one that's worth investing and have a higher chance of success at the end. So being in the centralized AI team gave me a unique perspective because I can see how the project was selected and executed. Throughout the year, I was able to work on many different types of projects across different business lines. I worked on for equity researchers, we worked on a special news recommendations system, and we also worked on capital market stock price prediction problems. And from all of that, there's a clear winner. The biggest success for the entire company and also for myself is this project that we built a self-explainable predictive model for the personal banking or personal and commercial banking space of the bank. Due to confidentiality, I can't tell you about the details of how the solution looks like. But if I look back, I can see 3 very key factors that lead to the success of this project. The first one is that this project is directly related to a team inside PNCV. For the people who are working in bank system, you might know this is one of the largest chapter that earns the money for the bank. So there's a strong drive from the company's perspective to do something different here. And the second factor is about maturity. The model we're developing is part of an end-to-end system that has been sitting there and serving the bank for more than a decade. So there's a lot of historical data being used, a lot of monitoring and reporting being there. So for us to ship this model to production, we don't need to build something end-to-end. We need to swap the model, and that's it. And the last one is the ML feasibility part. The original model that the bank is using is a fairly simple model. So with the more sophisticated technologies these days, we're fairly confident that if we're going to try some new model architectures and some new features, likely we're going to find a better solution. And all these 3 factors, I think, are the key ones that contributed to the success of this project. Reflecting on this, I don't think there is any fancier reasons why this is a successful project for us, and it's not pure luck for sure. The best machine learning projects are the ones that hit the sweet spots. The three components that I think are important are profitability, desirable to build from the business stakeholders, and feasible to solve from the technical perspective. By finding those opportunities, you'll be able to start your team with some winning directions. But finding those opportunities are not that straightforward. Often you need to ask some really good questions to your team to understand what's the situation. For example, is the goal clearly defined? And can your potential profit justify the cost you're going to put into the machine learning project? What assumptions are you making? And are they even realistic? And what type of risks your model might expose ourselves to? So don't be annoyed by your team if they keep asking these questions before they committed working on the project. The more of these questions you'll be able to answer, the more likely you are able to identify the right problem for your team to solve. Of course, this doesn't mean that we shouldn't take any risks. As you can see from the chart here, for high impact and low risk projects, these are considered as low hanging fruits for us to start our ML journey with. But the high impact and high risk projects are also worth pursuing. The key is to be aware of the risk that we're taking and build a balanced portfolio on top of that. Only if we have a balanced portfolio, you'll be able to allow your machine learning team to take some wins and then continue their iterations on building machine learning solutions. This also allows you to justify the cost that the company is putting into the AI infrastructures and all the AI talents they're hiring. But we also need some high-risk projects to be there because we want to make sure that there is a chance for you to be able to build some game-changing solutions at the end without any winnings in the short term. To summarize, starting a machine learning project just because everybody else is doing it or because technically it's feasible is not enough. We want to take time to collaborate with different teams to make sure that the project we choose is desirable, profitable, and feasible, and start well and lay the good foundation for our team. The second problem I want to discuss about is the challenge arise from data. This is probably one of the most common pitfalls and the one that your team complains the most about. Where are the data? Can we deal with large amount of data processing? Even though the company already invested a lot in solving those problems, it doesn't mean that there's no other hidden challenges that will make your project hurt at the end. There's a famous saying in the machine learning world, garbage in, garbage out. Machine learning projects depends entirely on recognizing pattern from the data. So if the data is flawed, then highly likely the conclusion you find from this study won't be trusted. So on the right, there is an illustrative example for your intuitive understanding why this data problem can be an issue. So the example is, let's try to find average points to represent your entire data set. On the top is the one that without removing the outlier. As you can see that the average is being dragged into the direction of the outlier. That may not be a good representation of general data. And after removing the outlier, you'll be able to get a better results. And that is just a simple example show how crucial it is to do some data cleaning before you run any learnings on top of that. Over the years, the machine learning community has developed some standard structure for data pipelines, starting from data collections, data processing, and to feature engineering. There's also a list of common tasks that people usually do for doing their data preparations, starting from data filtering for duplications, outliers, filling in missing data, to resampling your data to deal with imbalancing issues. So every proper machine learning team right now basically adapt these standard procedures for them to go over their data. But this is merely scratching the surface and is far from sufficient. Why is that? So if you're interested, there's a GitHub repository called Failed Machine Learning, and you'll be able to see a long list of failed machine learning solutions that people have identified that also are publicly available for everyone. The majority of these cases failed because of a reason related to data. Even though all the solutions are developed by big tech companies or the university researchers, supposed to be machine learning expertise, they cannot be immune to mistakes involved data. So this is on the slides. This is one of the examples. This is a study conducted by University of Princeton back in 2022. They did a closer look into 22 papers, peer-reviewed, that contains critical pitfalls that compromise the results. These pitfalls results are being adopted by more than 290 papers across 17 different fields. That means those kind of problems are very severe for us to take a look before it hurts something really important. So one key issue in every flawed paper is that it's partially related to data leakage. So in this simplest form, data leakage means that for some reason, we might take part of the test data into our training data and gives the model a false sense of success. But in reality, the definition of data leakage is way more complicated. Just like listed in the paper here, the researchers from the Princeton University are able to categorize the data leakage into 8 different type of categories, starting from mixing your training data and testing data to sampling biases and even beyond that. So it makes this complication of different types of data leakage makes it hard for us to identify it early on and prevent it from the beginning. Another example that we're seeing on the slides is in the AI in healthcare field. So I don't know if you remember the early day of pandemic when there's a lot of AI headlines making the news headlines saying that they're able to identifying or diagnosing the diseases. This is a proud work for many of the machine learning practitioners. However, the researchers from UK did a hard look into the studies that are being published. Among 606 models that claim that they can do diagnosis of COVID, only 2 of them have a good enough result that can be trusted and move the test stage. This is even before the clinical usage. And all the other models are completely useless. The main issue is, again, data related. Among all the 600 models, more than 400 of them are being trained on an inadequate sample of data and will draw some biased conclusions. That's why we won't be able to trust the results and conduct the process further. It is another harsh but essential lessons we learned that how the importance of the quality of data and how it might hurt your machine learning projects. Data preparation work usually feels like exploring an iceberg. What you see on the surface is just the beginning. Many problems, especially the one related to your own data, is hidden beneath. However, there's a couple of key questions you might be able to ask yourself to try to eliminate some of the risks. Are you collecting the data that's representative of the real-world data where your model is being adapted to? Have you avoided the risk of leaking future data into your training data? These 2 points are what we covered from the previous examples we looked into together. But the challenge didn't stop here. In large organizations, data silo is also a big problem. Teams may not be aware of what all the features we're able to use for training a model. This will lead the team to draw a wrong conclusion that the problem may not be able to be solved. Rather than that, it's actually there are some data that's underexplored. And finally, there's another big topics that we want to cover, which is label data. Labeling data plays a critical role in machine learning. For model learning perspective, we need the label data to extract the signals and optimize the model on top of. And from the evaluation perspective, we need the label data to understand how well the model is performing and where the problems are, so we can iterate on fixing those issues. Even though there are third-party vendors right now providing a lot of AI model data labeling solutions, trying to make this line of work more seamless, this still requires a large amount of effort from your own team. Usually, we need to collect and label a golden data set for us to use to evaluate the quality of the annotation we got, and providing a really detailed guideline for the annotators to follow in order for them to give ourselves concise labeling results. Even after all this prevention works, at the end of the day, you might be able to find that the label data is still lack of some consensus and you can't use it for model training. And I'm sure if you have worked on a data labeling work before, you understand a lot of the frustration behind the scene. This challenge becomes more interesting with the rise of model as a service or all the available pre-trained model. As the diagram show on the left, right now with the model as a service, we're able to actually skip model training entirely by just calling an external API or use some pre-trained model that works pretty well on their own data set. And this definitely allows us to deliver a solution faster than before. I remember attending a community discussion early this year, and everybody's working on some Gen AI solutions. And the question was, how are you evaluating your LM solutions? And the answer is that the first reaction from the room is that everybody went on silent. And at the end of the day, what they said is that early stages, they're just doing human eyeballing. Or they started to collect a small set of the examples for them to do some testings on the simple statistics, so they have a rough understanding of how well it performs. This is okay to begin with, because at the moment, everybody is in the fear of missing out mode. We want to push some Gen AI solutions out from the door. But it becomes a big problem later on. Because without the label data for you to understand how well your model performs, you'll keep adding patches reactively. There will be some downstream use cases or your clients complaining about a specific use case, so you add something to fix that problem without knowing how it's going to impact what's the broader impact of that patch on the entire data set. It also prevents you from collecting a good amount of data to doing your own model trainings that might be able to solve a lot of headache for you in the future. Later in this conference, and even before, you'll see a couple of them related to LM evaluations, and you'll see why this becomes very painful with the generative AI. But in my opinions, maybe to begin with, we can skip that step, but at the end of the day, we still need to invest a huge amount of effort into making this evaluation pipeline in place. Okay, the conclusion of the second component. While it's impossible to fix everything perfectly from the beginning, it still can't be emphasized enough to take the time to explore your own data, understanding your own data. Looking for new features, clean up your data set based on the observation instead of applying standard process to it, and investing in collecting high quality labels. In the end, machine learning success depends heavily on the data. The third problem I want to highlight is the challenge of turning a machine learning model into production. This transition isn't just about deploying the code. It requires a lot more context and from multiple times to make this solution come true. Of course, a significant amount of this challenge comes from MLOps, and many of us reference to Google's iconic diagrams to show that point. You can see that how little the fraction of the machine learning code is within this whole system. Majority of the code comes from the supporting infrastructure, like resource management, serving systems, monitoring tools, logging, and so on and so forth. For those of us who have worked on machine learning projects, this probably feels like hit the home. Fortunately, the landscape of machine learning ops has grown a lot, so there are so many resources available for us to tap into. Of course, for the first-time adapters, this sounds like a heavy lifting, but when you gradually start to build your own foundations and your own pipelines, it makes you're able to support multiple machine learning solutions and deploy them seamlessly than before. To understand the gap between a machine learning model and the machine learning-based solutions beyond MLOps effort, let's use retrieval augmented generation, or RAG, as an example. In the era of Gen AI, RAG has gained a lot of attention. Essentially, what it does is that it's trying to help you extracting context from your own database and asking your LM to answer the question with awareness of this context. The best part is that nowadays, this is how much work you need to work on a demo locally running on your machine. We just need to leveraging some OpenAI APIs, some launching libraries, and a vector database, and you'll be able to query your own database and asking a question. But when it comes to a fully functioning RAG system that supports production, for example, for customer service use case, for example, is an entirely different story. Here on the left is Gen AI system architecture that one of my favorite bloggers, Chip Win, summarized after reviewing many companies' Gen AI solutions. For production solution, there's a long list of aspects that you need to ask yourself and fill in the blanks. For quality control, What are the ways that you're doing quality evaluation? Do you need advanced RAG technologies or agentic RAG to improve the quality, or the naive RAG is good enough? For customer trust, do you need to bundle your solution with the explainability model so your customer knows how the result was generated instead of treating this as a black box entirely? For latency reduction, are you doing any caching? And if you're hosting any large language models locally, do you do any inference optimizations? This list goes on towards data privacy, towards how you're doing fairness and bias tests to make sure you're doing responsible AI, and also towards security, how you're handling the hallucination and jailbreak problems that everybody talk about in the GenAI world. In summary, a winning machine learning project team should be cross-functional, working closely together to form at the very beginning. They should actively align on requirements and resolve this issue step by step, instead of just working silo and hoping that all the problems will be fixed later on. Number 4, offline success and online failure. This fourth common pitfall is probably the one that's caused most emotional waves with the team. When you have a pretty well working offline model and then you ship this to production, all of a sudden it's not working anymore. So why this situation happens? To understand this better, I would like to show you a diagram regarding about offline training and online serving. If you can take a look at the left side, you can see that this is what happened during offline stage. We're using historical data to train our own model and evaluate it using the offline evaluation metrics. Once the model is deployed to production, we're using real-time data and going through the end-to-end solutions and evaluate our performance on the online evaluation metrics. And with this context in mind, you're probably able to see clearly where the 3 discrepancies might coming from. First of all, the data we're using is different. One is the historical data that often goes through some samplings and cleanings or augmentations to change the entire structure of the dataset. Well, on the production side, we're using real-time data to do the inference. And the second discrepancy comes from the solution itself. The team usually focusing on developing a single model rather than looking at the entire end-to-end solution that we're using in the reality. And the last one is the evaluation we're doing. For offline training, we're using offline evaluation metrics that closely work together with machine learning. Well, at the online stage, we're using online evaluation metrics that's more aligned with the business metrics. Let me share you an example. This is the first production launch that I had many years ago. So a few years ago, we were working on a photo recommender system that aimed to promoting photographers' work to a creative photography community. One of the main worries our business have is that our new users shopping is they come here, register, publishing 1 or 2 photos, and they never come back. With that in mind, our data science team started to do some explorations and trying to find out what's the problem. They find a high correlation between how many likes a new user will get within a short period of time after they register to this new user retention rate. With that insight, a machine learning team is being asked to promote the new user works as soon as possible so they can get the reaction they wanted and come back to our website. At the time, most companies are still relying on relatively simple recommendation system, often powered by this technology called collaborative filtering. The intuitive understanding is shown in the diagram. For user A and user B, if they liked a lot of the same items before, we consider them having the same taste. And then after that, we'll try to find the items liked by user A but hasn't liked by user B and give this as the recommendation for user B. This also will explain the reason why our new users don't get a lot of likes, which is called co-star problems in the recommendation system. So because of the new items didn't have any visibilities or any interactions before, and the recommendation is purely based on the previous reactions of a photo. So the new photos, it's really hard for them to get the first bunch of reactions and get the row started. We decided to build an additional recommender engine to accommodate the co-start problem that the collaborative filtering solution bring in, which is called content-based recommender system. What we do is we trained a classification model offline, trying to predict how popular a photo would be purely based on the content of the photo itself. In that case, when a new image comes in, we're able to identify whether this will be popular or not right away instead of waiting for the signals to come in. And once we have a good model performing for this classification task, we integrate it into this pipeline. For user A, we're able to extract the historical behaviors of that user and find similar photos that the user liked before. These similar photos the user never seen before will be filtered down by this popularity identification model that we built. In that case, we're trying to reducing the chance that the low quality photos will be recommended to the user, while keeping the content to be relevant to what they liked before. Offline, what we optimize is the classification model. We're trying to predict the popularity of the images and see what's the accuracy we'll be able to get. But when integrated into the model into the production system for A/B testing, we have some mixed signals. Well, the number of likes new users did receive, which we achieved our tasks in some ways. We also received some warnings from the major dashboard that were used to monitoring the health of the platform. We saw there's a drop of the average session length that our user is staying on our platform. Means for some reason, our recommender system is causing a disturbing experience and they don't want to keep scrolling our website anymore. This is a tough situation. And because it's my first launch, I remember feeling very anxious when there is focus group feedback rolling in, criticizing about what we built. It was a challenging moment. We went through many rounds of iterations and eventually find a better way of incorporating this popularity prediction signal into the system. But that was a long story afterwards. And what to add is that the recommender system today have become way more complicated. For people who attended the Netflix talk before, you probably already see the diagram they have shown you. There's so many models that are being involved for a single recommender system. And there's multi-steps that we're going through for making this happen. Besides the difference we talked about between offline evaluation and online evaluation, and also monitoring a set of business metrics instead of just the single one primary business metrics we're trying to optimize, there's an additional complications. So once a model is integrated into the production, it becomes part of the entire solution, a much larger system. We're combining output from many different kinds of models. So an offline model that performs pretty well after the incorporation, because the model's output are not orthogonal to each other, the impact of that model may be diminishing after this merging. After we see there's so many ways why the offline failure can offline success can turn into failure, the point we really want to make here is that what we want to emphasize is not to stuck on over-optimizing incremental succeed in the offline models. What we really want to do is to allow the A/B testing to happen as soon as possible. So we can use this to test it out if our optimization target offline is well aligned with the business goal we're really trying to optimize for. And the last point, which is one that often get overlooked, is unseen non-technical obstacles. Is the non-technical obstacles really a big problem? This isn't just my opinion, it's also backed by data. So going back to the survey that we looked into before, when people were asked a very straightforward question, what are the main obstacles to deploy models at your organization or your client's organization? Interestingly, the most common answers people get, the top two, are not related to technology at all. The first one is that decision maker or stakeholders are unwilling to provide the support that the project needed. And the second is they have a general lack of active planning. These are not technical roadblockers. These are organizational and communication blockers. Why managing stakeholders is tricky? Well, although there's a lot of enthusiasm for AI, especially from the leadership perspective nowadays, it doesn't guarantee that the decision makers is able to make the right decision. The truth is that many stakeholders doesn't have AI backgrounds before. So they might be influenced by hearing a lot of the news that how AI is making the big impact and making the big wins for the company without aware of the risks and the failures they might cause. Also, they might be biased by their own experience managing non-AI traditional software engineering projects in the past. This is where AI experts actually play a role. It's not just about building the model. It's also about making sure your stakeholder understands what is the right expectation to set for your AI projects. Some key topics to explain might include how AI learns, so they know that why there's a heavy dependency on the data and why we should invest heavily into the data process pipeline. Second question, why machine learning projects are inherently uncertain, so they know that what's the potential risk that the project will fail at the end. Third, the limitation of the models. So we won't launch a model to production without the business stakeholder means the potential reputation the uncontrolled output might bring to the company. And the realistic cost of building and deploying them, so the stakeholders can justify whether the cost can be justified by the profit. Now let's talk about how to manage and plan these projects. There are 3 principles that really stand out. First, scope out a minimal MVP with a clear and simple optimization goal. This helps the team to get focused and starting doing their work without reducing their noises around the space. The truth is that starting with a simple baseline model can actually be a better situation than if you start with a more complicated model. Second, once you have MVP outlined, prioritize building an end-to-end solution so you can allow your team to do A/B testing and getting the production feedback in place as soon as possible. And finally, using these feedbacks to iterate and adapt your projects quickly. This might need you to redefine what's your project optimization targets or adding more data into making your model better. One of the most effective strategy I've seen in the past is outlined here. There is a separation between a project incubator and the product line. In the project incubators, we can do early stage, high risk idea testing. So we use this as bets to figure out which are the models that actually worth us investing longer term and form a full stack team to work on in the longer term. This approach allows your team to do innovations and while managing the risk carefully. The key takeaway here is that managing machine learning projects is different than managing a traditional software engineering project, and we need to adapt to these kind of major challenges to make sure your team can get the support from the non-technical perspective. And with that, we've covered the last common pitfalls I want to share with you today, along with some strategies to avoid it. To quickly summarize that, while there's no way to guarantee we'll avoid all the mistakes, there are some principles or best practice we might be considered in reality. We want to choose a project that is feasible, desirable, and profitable. We want to be data-centric. We want to encourage early collaboration and active management of cross-functional teams. We want to build an end-to-end solution soon for testing purpose. And we want to adapt your project management plan based on the nature of machine learning projects. Honestly, this is just a very incomplete list among a lot of other reasons that why a machine learning project might fail. But I hope this can be a good starting point for us to kickstart the discussion. And I definitely love to hear about your own experience and what happened to you in your own projects too. Before I close, I'd like to leave you with a favorite quote of my own from Charlie Munger: learning everything you possibly can from your own personal experience. minimizing what you learn vigorously from the good and bad experiences of others, living and die. That's wrap up my entire presentation, and thank you all for listening.
All right, we have time for, I think, 1 or 2 questions. If anyone has any questions, we have a volunteer that'll hand the mic over. I guess I can start with one question, which is, you mentioned in your talk those business metrics that are used for evaluations. Could you maybe give some more examples of those business metrics? As you mentioned, I forgot if it was like retention or session length, right? But what are some other common ones that are being used in your experience?
Yeah. So there are 2 types of evaluation metrics I think we should pay attention to. One is specifically about the thing we're optimizing for. Like, for example, at Grammarly, we're doing the rewrite suggestions. So one thing we definitely cares a lot about is the click-through rate, like how many, accept rate, like how many of the suggestion we're giving got accepted by the user at the end. So we know it kind of reflected on the quality of the suggestion we're giving. And the other metrics are like more towards the major health of the entire platform, right? Like how many people are buying Grammarly's memberships, and how many times they're using Grammarly's, for example. This is similar to all the other use cases. Like, you want to make sure whatever you are optimizing for is not hurting the major business that your company is focusing on.
Hey, I am Vici, founder of Maxim AI. One of the things you mentioned, the importance of evaluation in the life cycle. I'm just very curious to hear, how are you seeing the roles evolve? Like, in traditional MLOps, evaluation was always like machine learning team, and now kind of the roles are blurring in terms of ML engineering, software engineering, also like PMs being more involved in the life cycle. So who do you think is more responsible for evaluation more broadly? How are you seeing that evolve?
I think the one I see before is that works best before is a combination. Like, for example, the unit tests. Like, machine learning people don't do a lot of unit tests, but nowadays it's actually pretty helpful. Like, if you can collect a bunch of like examples that really valuable to your company, and when you're doing model iteration, you want to check all these tests are still passing. But also, there's also like machine learning metrics that we can use to evaluating the model. And some of them can be automatic, this are statistic based. So in our team, like linguistics will be the one working on those automatic metrics. Some are like learned evaluation metrics that are more state of the art or recently published. And these requires like paper ratings and the implementation and experimenting before we push this into our major monitoring metrics. And these mostly requires machine learning people to get more involved. And at the end of the day, we'll use like a combination of all these tests to make sure that things are going well.